Good evening, everyone. Trust you're all doing well and are taking good care of yourselves and your near and dear ones. Welcome to the fifth session of Scientifically Speaking Season 4, a public engagement series that aim to connect high school students and anyone who is keen to learn with interdisciplinary scientists exploring complex problems. My name is Bhavesh and I'll be your host for today's session. I'm currently a computer science PhD student at Ashoka University. So without much ado, I'll quickly introduce our speaker for today. We have with us Professor Sudhindra Hangal. He is the visiting professor of computer science at Ashoka University. Professor Hangal earned his PhD in computer science from Stanford University. His research focuses on the area of human-computer interaction and personal digital archives. Professor Hangal has also worked on multiprocessor computer architecture, virtual machine compilers, software engineering, and debugging tools. Professor Hangal also holds a BTech from the Indian Institute of Technology, Delhi, and an MS with distinction in research from Stanford, both in computer science. In today's session, Professor Hangal will talk about what makes a great programmer. How is programming similar to and different from other disciplines that require great skill and excellence? Is it an analytical or a creative discipline? He will present some philosophical musings on these questions and the practice and profession of programming. Before we begin, I would request our audience to type their questions in the Q&A box. We will address them after the talk. On that note, I would like to invite you, Professor Hangal. We are very excited and look forward to your session. Over to you, sir.
Thank you, Bhavesh. Can you see and hear me?
Yes.
Okay, let me just share my screen. Yeah. So thank you, Bhavesh, for inviting me to this series of talks. I've watched a couple of the earlier ones and they've been really interesting. I apologize in advance today. I have a rather scratchy throat, so I may not sound very good and I may need to sip some tea in the middle. But what I wanted to do today with all the high school students, undergrads and others is to reflect a bit on what it means to be a great programmer. And I'll say that I don't necessarily know what it means, but I can share with you through my experience of about 35 years. I've been a programmer for about 35 years. Like many of you, I started as an undergrad in computer science, writing programs. And to this day, I still enjoy writing code. I love the idea of creating something with code. I love the idea of starting with with a blank sheet of paper and starting with the main program and then seeing where it takes me. So over the course of my career, I've worked in all kinds of companies, both in hardware, software, now in consumer-oriented systems. So I've been lucky to build many different systems or been a part of teams to have built many such systems. But I've been humbled by how many errors I've created along the way. I've been humbled by how difficult it is to get even the simplest programs right and how tricky it is, and therefore how challenging and interesting this discipline actually is. So I hope to convince you or at least share with you some of my perspectives on the field of programming in general today. So before we start, I'd like to show you a couple of examples of great programmers. I picked a few at random, but obviously the list is very, very long. On the left here, you see Don Knuth. Many people think of him as the father of computer science, actually. And he's had an enormous impact on the field. He's not only developed algorithms, but he is very well known for a couple of very famous typesetting programs, TeX and LaTeX, which are used extensively by the scientific community, not just in computer science, not just in engineering, but in many, many disciplines. So he's sort of the prototypal computer scientist, if you will. And on the right, I've put Bill Joy. Bill Joy was one of the pioneers at Berkeley of Unix, which, various versions of Unix underpower all the modern computers, and Bill Joy really built upon Unix, which had been developed earlier at AT&T, and built a version of it that was much more usable. Of course, is also well known for many other contributions like the VI text editor, and he was instrumental in the Java programming language getting the widespread adoption that it did. A couple of other examples. Sanjay Ghimawat and Jeff Dean are very well-known senior programmers at Google. They've sort of built a lot of the technical infrastructure at Google, or been responsible for it. And some of their work has been very seminal in the way we build clouds and compute services today. Some of the revolution in computing cloud away from mainframes and high-end server hardware to much more scalable, much cheaper clusters came through some of their work. In particular, a couple of papers they published about MapReduce and the Google file system back in 2003 and 2004. And from then on, the whole field of cloud computing and this thought of computing as a utility has really taken off. If you want to know a bit about how great programmers think or work, I highly recommend this article from the New Yorker. It came out about 3 years ago, I think, which profiled these two star programmers at Google and went sort of a little bit into their lives and tried to understand how they work together and what kind of problems they solved on a day-to-day basis. So I do encourage you to read this article if you can. But what I'm going to do in the rest of the talk is to try and distill a few tips from my own experience of what I think some of these great programmers have done very well, and how I think the young people today should be thinking about programming as a job, a skill, a discipline, a career. So the first thing I'll point out is to be a programmer nowadays is a very, very serious job. So you need to take it very seriously. Programming is sort of, or software and computers in general, underlie much of our lives today, right? So you can think of during lockdowns and so on, many times there were cases where we could afford the electricity going down, but we couldn't afford the network going down. We had to be connected for our calls, classes, and so on. So computing is really a vital part of the societal infrastructure today, which is not necessarily the way it was 20 years ago. 20 years ago, you could still say, if there's a problem, let's reboot the machine and restart and move on, right? Now that's no longer possible today. The infrastructure that we depend on is extremely important. It's often mission critical. It could even be safety critical. And so we have to think much more like other engineers have for many decades now. So imagine somebody building this bridge. They're obviously paranoid about collapses like this, which do happen, and they go to great extremes to make sure that this kind of situation doesn't happen. Of course, it's not just about building the bridge, it's also inspecting, continual maintenance, and so on. And that is the attitude and mindset that we need for building software today. Okay. What that means for you is, as a programmer, or for all of us, is to take our job very, very seriously and imagine that a bridge could collapse someday because of some defect in our work. Another set of professionals who think like that might be doctors and surgeons who treat people, cut up people, and operate on them. I'm giving you an example from a nice book called Complications by Atul Gawande, who's talked about how different or difficult life changing decisions, life-saving, life-threatening decisions, surgeons have to undergo every day, and how seriously they take those decisions, right? So working on a piece of modern infrastructure means that people are going to depend on your programs in ways that you probably did not anticipate and may not even have imagined. But what you do does affect a lot of people now, and not merely the technologically connected or the technologically advanced, as was the case maybe 20 years ago. The second point I'd like to make is to be very, very skeptical and critical of your own thinking. When you're writing a program, do not look to confirm what you're thinking. Do not run through your logic, the same logic that you thought of when you first wrote the program. If you're rereading it, try not to think of why the program is correct. Try to think of why the program is wrong. In fact, assume the program is wrong and look precisely for the reasons why. And the reason is that programming is a very, very tricky discipline. To illustrate that, let me show you a small proof that, maybe if you're in 11th or 12th, you might already have seen. But it's a bunch of algebraic manipulation that shows 1 is equal to 2. I'll let you absorb it for a bit. And then maybe you can tell me what is wrong with this proof. I don't know if people can type in the chat, but you might have seen this is just straightforward algebraic manipulation, right? Most of it seems to be very straightforward. But at the end, you have a problem. You have, excuse me, derived or proved a fallacy 2 is equal to 1, which obviously cannot be true. Suryan mentions multiplication by 0 on both sides. So he's correctly pointing out that over here, when the fallacy is in this step, where a plus b into a minus b is equal to b into a minus b, and then you're canceling the a minus b and leaving out the a plus b equals b. Now that cancellation of a common factor can be done only if that common factor is not 0, right? So there is a tricky thing to keep in mind when you're applying the rules of even elementary algebra like we're doing here. So mathematicians are very aware of how subtle these proofs are. And here it was just about 7 or 8 steps, and it was easy to spot the error. But in a more complicated system, proofs can run into hundreds of pages, or they require lots of lemmas and theorems and intermediate steps and so on. And you have to be very, very careful about the assumptions you're making. And programming is somewhat similar in the sense that large pieces of code, large programs are essentially proofs that are proofs of some property or the other. Often you don't know what that property is even, but you have to identify that property and then you have to prove it correct. So a lot of programming is about proving things to be true. Okay, so I just want to caution you that in programming or in proving, it's okay to be slow. It's a minefield out there. If you rush too fast, you will probably make a mistake. And therefore, it's very good to go step by step, have clear reasons why one step leads to another, and constantly be looking for problems like the one we had earlier of the division by 0. Constantly be aware that there might be some case that you're not considering in your program, in your code, that may come and destroy your logic. Okay, so a lot of programming is about taking a program, taking some piece of code, and then thinking of what are even the proofs that are embodied in the code. What are even the specifications embodied in the code, and then what are the proofs that the code performs to that specification. or in looking for a proof, you may come up with bugs that the program actually does not do the correct thing that it was meant to do. Okay, so this is one of the most interesting properties in writing complex programs. You have to basically identify the invariants in the program, document them to yourself, to others, and then prove that the invariants are true through all possible paths in the program. And even a moderate size program like a 100,000 line program will have, an uncountable number of paths through the program. So if you have to prove that some property is assured to hold on all possible paths through the program, then that requires a lot of proving skills. So if you do complex programming, you will be doing a lot of proofs, whether consciously or subconsciously. But it's good to be aware of it consciously and to think of it like a proof and to apply the same rigor and care that you would apply to a math proof. Another example I can give is, let's take a game like chess, an adversarial game. So when you're programming, it's good to think about as if the inputs that your program is going to see are almost adversarial. They're trying to find that one path in your program which is going to cause the program to fail or to crash, and therefore you have to be paranoid. You cannot just like in chess, you cannot assume you solve the problem just because you make a move and you hope that the other person makes a weak move. No, you have to make sure that whatever your move is, it works against all possible responses by the opponent. And that's what makes games like chess very interesting. And that's what makes programming very interesting. Okay. Remember, your proof is only good as its weakest link. So even one minor corner case that you forget is likely to cause problems and likely to be very expensive in terms of the cost of a software crash or an outage, etc. Tip number 3. Conceptualize something grand and build it in layers. So if you think of some great idea, you cannot attack it you cannot attack it all at once. So the way to tackle complexity is to build in layers. And imagine you come up with a beautiful architecture like this. And in many ways, programming is very similar to architecture. You think of something grand, but then you have to, sort of put a lot of bricks in place to make sure you get to that grand vision. So programming is fundamentally both creative and analytical, just like architecture is. There are many creative and different ways of building something, whether it's as a building or as a piece of code. For example, let's say Ashoka University and IIM Bangalore. They're both universities, but their architectures are completely different. The buildings are completely different because they have different contexts, different realities, slightly different purposes, slightly different histories, and so on. So there's a lot of there is a lot of vision that goes into constructing a building architecture like this. And similarly, there's a vision that goes into building a program. Not all programmers will build a program the same way, even given the same task or the same specification. And that's why programming is also a very creative task. But once you've created a design, you do need to spend a lot of time in going into the detail and making sure that everything really is in place and is consistent and so on. So there is a bunch of very interesting vision work at the beginning, but then there's a lot of detail-oriented implementation work to build the actual thing. Another important thing in if you take buildings is that you have to build them on layers, right? You have a foundation, you have a floor, you have another floor. You have a complex like this, which consists of different buildings that kind of interact with each other. And programs are very similar. We think of different layers in a program, or even in computers in general. We have about, depending on the complexity, we may have 7, 10, 15 layers. But there's actually this famous study in cognitive science by George Miller from the 1950s, which showed that humans have a cognitive working capability of about 7 items at a time. It's called the 7 plus or minus 2 rule. So at any given level in a very complex system, you don't want more than about 7 or say 9 items at one level. If you have 50 items at one level, that's too much. And the way I translate that rule for programs is that you could have a 1,000,000-line program, but it has to be structured as units, as levels where there are no more than about 7 to 10 units at one level. You think of even our entire computer systems, which are so complicated, are sort of like that, right? You have transistors at one level. Then you have an architecture, a microprocessor architecture that takes that and exposes an instruction set. You have an operating system that takes the instruction set and exposes some higher level functions. Above the operating system, you may have, maybe a virtual machine layer or a runtime layer, and your program runs on top of that. And each of these layers doesn't look into the details of what is happening inside the others, but it just deals with the interfaces, right? So creating these interfaces, creating the breakdown of a massive grand vision is sort of core central to programming. Another analogy I can give with architecture is think in terms of evolution. Buildings live for a very long time, hundreds of years perhaps. Software, in my mind, great programs live for a long time, although it's hard given the pace of change in the computing industry for a program to even live for 20 years. I think the most that any program of mine has lived and been useful for is about 15 years. But in general, you have to think about not just about building it one time, but about how the program is going to evolve, how the needs are going to change. That's a very important part of building programs, anticipating problems, and how do you fix it when something goes wrong? Just like in a building, you need all kinds of, you have chutes and shafts and various tools for diagnosability. You need the same thing in programs, right? If you design a component for one building, can you use it somewhere else? Can you have reuse? That's one concern. Is it environmentally friendly? That's becoming an increasing challenge, even for programs, just like it is in buildings, right? So I think architecture and programming actually have a lot of parallels. My next suggestion is to be very, very organized. And I'll give you an example of, a professional kitchen. And if you see how a professional kitchen is organized, or how even your own kitchen may be organized, things that are used very commonly, very frequently are probably near your stove. Let's say you make chai 3 times a day, then you will have your, tea leaves and sugar and whatever else you need for it right next to the chai. But whatever you don't need so often, you will put away in a pantry. And that is basically, the idea of a cache. And similarly, if you have 4 burners on your stove, you have the idea of parallelism coming there, etc. So, many of these ideas that are core to computers and programming, pipelining, parallelism, etc., are common sense ideas that you use in your daily life. How do you retrieve something? So, when you're doing programming, you should ideally keep a focus on high throughput. Imagine a restaurant that's serving a lot of orders at lunchtime. Obviously, they have to be very efficient because customers don't want to wait very long. They have to maybe prepare whatever it is that's possible to prepare in anticipation of demand, so that they can reduce the latency of delivering an order. And they have to keep many things going in parallel, and so on. right? So if you apply that same focus to programming, um, you would ideally look for efficiency everywhere, even if it shaves off only a couple of seconds somewhere. Um, the couple of seconds matters a lot at scale, because if you have a billion users using your program, uh, that's a lot of seconds, and it's a lot of overall saving if you can optimize the program. Similarly, other things we can learn from um, professional chefs, let's say, is that use the best tools. Right? They have the best tools that will allow them to perform actions quickly, predictably, avoid burning dishes, things like that. So even in programming, we should use the best tools. So the best programmers use the best tools and even build their own tools if one doesn't already exist. As a professional programmer, just like a professional chef would keep their kitchen clean all the time, great programmers keep the code neat and clean, even when no one is looking, by the way. So it doesn't have to be just for code review purpose or whatever. It could just be for your own satisfaction of having a neatly organized piece of code. You may want to clean it up, write comments in it, and so on. So be very systematic in your approach to programming, whether you're looking for a bug, just cleaning up code, writing documentation, etc. One of the delightful papers Don Knuth, who I mentioned in the first slide, wrote was about his analysis of the bugs in the early versions of tech that he had written. And you can see how systematic he was in just noting down every single mistake he made himself, and classifying those bugs so that he could train himself to be a better programmer and avoid those kind of bugs the next time, right? So being very organized definitely is a facet of great programmers. And my last quick tip will be to be very, very social. People have this misconception that programming is a very solitary activity. Actually, it's not. Programming is actually a very social activity. Most of the work we do today are in teams. Most of the time we depend on code that's written by others. So we are, or others are depending on code that we write for them. And so there's a constant process of communication. You want your code to be used by others, you have to make it user-friendly. You will be required to explain this code to somebody else who's going to maintain it for you later. Or maybe you have to leave the company and somebody else is going to take over that job. Are they going to be able to understand what you did? And so are they going to be able to enhance what you did? Right? Most of the work that we do in industry is actually enhancing programs that already existed or fixing bugs in them and so on. And so we are very, very dependent on the people whose code we work with. And so it's actually a very creative activity in terms of the social network that you form within programs. For example, I would encourage you to think of writing documentation as a creative activity and use your best creative thinking skills for it. It's okay if you introduce a joke in the code. It's okay if you introduce humorous examples or explicitly point out pitfalls, etc. You're kind of having a conversation with a future programmer who's going to deal with that code. By the way, that could be yourself. And if you're reading your own code after a year, you probably won't remember any of it. And it'll be as if you're looking at somebody else's program, right? So it's almost like a conversation with the future version of somebody working on the program, whether it's you or somebody else. Okay, Don Knuth has this great quote saying, programs are meant to be read by humans and only incidentally for computers to execute. This is the opposite of what many people do, which is to write programs and somehow make them work without worrying about how readable they are. And to pull a couple of quotes from the New Yorker article I mentioned earlier, it's talking about Sanjay Ghimawat's code. It's saying if you're looking at a file of code that he wrote, it's beautiful in the way that his sculpture is beautiful. When I want to add new functionality to his code, it seems like the hooks are already there, and his code is social, right? So I definitely want you to think of programming as an activity that involves many other people, involves relationships with many other people, soft skills with other people, and so on. And it's also, which other kind of writing do you have where there's some piece of writing and then suddenly it goes off and executes something else written by somebody else and then comes back? We don't do that in normal writing, right? A novelist would not say, here is a story, and in the middle, go read that chapter from that book and then come back here. Right? That's effectively how programs work today, and therefore they are inherently a very social and collaborative effort. Okay, so I'll just summarize the tips. Be very serious, be very skeptical, build things in layers, be very organized, and be very social. Okay. With that, I will stop here, and I'd be happy to take any questions that you have.
Thank you for such an enriching and engaging session, Professor Hangal. I like your analogy of how a programmer is compared to a chef. That's very engaging. Before we move to the Q&A, I think I will ask a question which many in the audience might have. So let me ask this first. Can you tell us more about the CS program at Ashoka? And then follow-up would be, how is it made different from similar programs at other such places?
Sure. So I'm a visiting professor now, so I may not be completely up to date with the current status of the program. But I was associated with the program right from the very beginning in 2014, so I do know quite a bit about it. So I think one overall point to make about CS at Ashoka is that it's embedded in a much broader university than a typical engineering or technological university is in India, at least. And so it's much more, I'd say, modern and interdisciplinary than traditional engineering-based programs in CS. For example, I myself have had a chance to work a lot with the political scientists at Ashoka. We run a center for political data there. Similarly, we have other people who work with initiatives in healthcare, social media, even COVID modeling, things like that. So I think the CS program at Ashoka is number one, very interdisciplinary, and number two, the overall Ashoka program is very broad-based. So unlike, say, the IITs where the humanities are mostly an afterthought, I think at Ashoka there's a lot of emphasis given to the humanities with the foundation courses, with the writing program, and so on. And therefore, I think students emerge probably better prepared for the workplace, apart from just their CS training.
Okay, thank you for that. We'll move on to the Q&A session now. We have curated a few questions from the audience, so I'll start. The very first question is about somebody who is just starting to program, and there are so many programming languages, programming environments, operating systems. For a beginner, it might be very confusing what choices to make, and do they affect the way programmers function?
Yeah, of course. I mean, there are so many programming languages and environments and all that. But I'd say start with something that you want to build. You don't start learning C or Java or JavaScript or Python just in a vacuum, because that's like studying bricks, for a building, different types of bricks to build a building, but you don't know what kind of building you want to build. So first decide the building you want to build. What is it? What program do you want to write? And then find the appropriate tool for that particular task. Some languages are good for certain tasks, other languages are good for other tasks. There's a lot of information online, you can find it, but I'd say start with the end goal in mind. Conceptualize this grand thing, and then break it down into the steps needed to get there.
Okay, great. So continuing from the previous question, do you have any favorite tools which you use often, or like they have helped you, doing your programming in a better, efficient way, or neat way? You've been focusing on that, yeah.
That's a good question. I'd say my favorite tools in general are debuggers. I've been using debuggers for a very long time. Started using DBX on a microvax system. That was the first debugger I used. But it was still a very, very powerful debugger. And today, I guess the browser inspectors are extremely powerful debugging tools. The inspector you have in Chrome and Safari and all these browsers. But it's really fun as a programmer to have access to a debugger. It's like having access to, say a CT scan or MRI scan. If you're a doctor, you really know what's going on inside, and you feel a sense of power when you can peek deeply into a program. So I'd say debuggers are definitely my favorite tools.
Okay. Next question is interesting in terms of this somebody from the audience asked, isn't programming essentially an important job in a world where data controls a large part of our life? What motivates a programmer to push on in such a stressful lifestyle? So, you answer that.
I don't agree it's stressful. Not necessarily stressful. Any job can be stressful or not. I actually think that it's many people, by the way, do programming for relaxation because they can deal with something that's predictable and controllable. Okay, so I don't think it's necessarily a stressful job. Of course, your particular job situation, you can't comment on that. I think it's absolutely true about programming is an important job because it's not just data, but just programs control our lives, right? We probably couldn't live without our phones or our laptops, at least in our socioeconomic class. And I think that's absolutely a truth, and it's only going to become accelerated. I think computing is becoming or has become a utility, just like electricity is. We don't think about it anymore. We just assume it's there. And if it's not there, then we probably don't even know how to function properly.
Yeah, okay. Next question is, would learning a new concept benefit from slow and thorough work, or just trying everything, like a quick and dirty approach?
So it depends a bit on the situation. By default, I'd say the slow and thorough approach is always better. But often when you don't even know which direction to go in, you need to sample a whole bunch of things. For example, you don't know any language. You want to try out 3 different languages before you commit to something and go in one particular direction, where of course then you need to be thorough about that language, right? So I'd say quick and dirty in the very initial stages, but then slow and thorough when you know which direction you're executing towards.
Okay, the next question is, are coding and programming different? And I'll add algorithm to it also. Are these 3 different terms, coding, programming, and algorithm? How do they differ? And are there any open source websites where the students ask where I can get hands-on experience for this?
So coding, programming, and algorithms, right? That's what you said.
Yes. Yes.
I'd say coding is the process of writing code, obviously. So that's the most specific of the three. Algorithms is, coming up with a specific method to solve a particular problem. And I'd say programming is sort of a composition of all of these, where programming literally doesn't mean just writing code, but it could also mean debugging, it could mean testing, and so many other things. So if you think of the kitchen analogy, right? The algorithm might be the recipe you use to actually, make a dish. But as you know, I mean, the kitchen involves so many operations other than just the recipe, right? You need to think of where your supplies are coming from. You have to think of, who's going to clean the kitchen. You need to think of, is your refrigerator working? If not, you have to go fix it. So there's a whole bunch of issues around managing a kitchen. And I think of programming as a mix of all of those issues, or a combination of all of those issues, whereas algorithms are very specific, stepwise steps to achieve a certain goal.
Okay, because you talked about, I think, large code bases and medium code size being 100,000 lines, there is a question on this saying, how do you organize such large code, and are there any tips to manage it?
Yeah, I mean, it depends on the specific situation, but I think the rule of 7 is a pretty good one. So, for example, if you have 100,000 lines of code, they'd be organized in maybe, let's say 7 packages. Each package might have 7 to 10 files under it, maybe classes or whatever your programming language supports. And each class may have, or each file may have, again, 7 to 10 functions inside it. Every function ideally would have no more than 7 or 8 blocks within it. So that when I'm looking at a particular piece of the code, if I'm debugging it or trying to understand it, I shouldn't have to remember too many things or too much of context to understand a particular line of code. Like that's where it comes from. Because if you have to keep a lot of things in mind to understand a particular line of code, that's probably too hard to understand. So the best programs, the most beautiful programs are the ones that are simplest to understand. And that you can do only by ensuring that there aren't too many concerns, too many things affecting a particular line of code.
Okay, so I think what I learned from there is keeping it simple in the sense that you have the minimum dependencies with other modules. The next question is it's about reading code. So I understand there are some codes, as you also mentioned, Sanjay, from Google, writing beautiful code and like piece of art. So the question is, it's sometimes said that reading code is fundamentally harder than writing it. How do we get better at reading code?
You try and read better code, better written code, first of all. It's an interesting question. How do you get better at reading code? I tend to think that the burden of that is actually on the writer, not on the reader necessarily. However, as you get some experience, I think you will have mental models of what the code is trying to do, even if it is not being explicit, because you kind of see the patterns, right? Just like, we train ourselves on patterns, and biologists might know, different kinds of leaves, let's say. And even if they get a fuzzy image, they might be able to identify that this is that kind of a leaf. So similarly, if even you're getting a fuzzy picture through the code, with experience, I think you'll get some idea of how, of what that code might be trying to do. But I don't think, I still think it's better to put the burden of writing good code on the writer and not on the reader. And that's why we have things like, code reviews, etc., where we make sure that our code is intelligible by some other person before we actually use it.
how does, like, this is my question, how does one select or get to good written code? So are there examples which you uh, have seen in the past that, oh, this is a piece of art, as for the Sanjay from Google you have mentioned? Are there something available online where student can see?
Sure. I mean, just like good books and movies, well curated pieces of software will be written well. So typically things from well reputed open source libraries will be well reviewed and edited and so on. So let's say the Apache tool chain or things like that would be very good. I would also recommend a particular book called Beautiful Code. It's a compendium of about, I think, 25 or so people who have reflected on particular code modules of programs that they've written. I think that's a very good book because it doesn't just take you through code, which is one thing, but it also gives you perspective. It gives you the writer's perspective on how they came up with that particular design or algorithmic choice, etc., or just organization of that code base. So that's a good thing I would recommend. But in general, I would also recommend instead of just using libraries, a lot of us use libraries all the time, right? Whether it's in any programming environment, much of our work is integrating things that existing libraries already do. I'd encourage you, particularly in open source environments, to look at the code that lies behind the library. So get some idea of the implementation of the library as well. And that will often help you use the library better, but also importantly, give you a sense of how these robust libraries are written. For example, I used to work at Sun when the Java libraries were written, and I think they're written very, very well. And so looking at how they, first of all, organize their code, but also think about all the possible cases, think of the invariants in the code, etc., is quite enlightening, and that's something you may be able to apply in your programs as well. So don't be hesitant to read code that lies behind libraries that you're using. Don't just be a user of the code. Don't hesitate to jump in and look at the code directly.
Yeah, that's so much out there. And the next question relates to that. Even though there are many sources available online, how does one venture into coding as a high schooler? And I think they mean, how do you sustain the practice, scale it and sustain it?
I'll go back to my previous answer, which is build something that you are interested in building. If you're interested in games, design a game and then see what tools you need to build it. If you're interested in music, build tools that will help you create something in that area. So just follow whatever passion it is and think of programming as a tool that will help you experiment with ideas in whatever domain you're interested in. And the beauty about programming and software is that it's so easy to use, right? Unlike a real architect where I have to think about getting materials and bricks and all of that. Here, you don't need anything more than, maybe a laptop at most. And then the rest is all completely up to your imagination. So it's a very, very creative and fertile medium. It's like putty, really, right? You can shape it to be anything you want. And so I think all you have to do is just find something you are passionate about and then start finding a tool that will help you build a program.
Okay, the next question is a bit specific. They want to know any suggestion regarding learning a programming language as a beginner to develop coding skills for data analysis in biology.
So I'm not very aware about biology and so on, but I think it's any data analysis. Nowadays, of course, that's a very important skill. So first of all, I think you need to know what the underlying sort of algorithms, right, or metrics in the data analysis. So how do you do correlation, or how do you spot anomalies, or how do you visualize something? So these are things that at a higher level you need to be able to think about for your particular domain. But certainly, I think nowadays there are a lot of good tools for data analysis. R and Python particularly come to mind, but I'm sure all languages have tools for data analysis, and of course, visualization, data cleaning, the whole data pipeline effectively. So, excuse me, I'd encourage you to try out one of those languages, again, working with real data. So you're solving a real problem, and then you find whether that's the right tool for you or not.
Okay, as you're saying, somebody who wants to start, they should be starting with a real problem. And again, question might be, how do you select one problem? But there are so many things out there, and it looks like most of the things which I can think of are solved, at that age. So how do you, or you just replicate something? What do you think?
That's a good problem to have if all your problems are solved. But I don't think we're anywhere close to solving all problems. I think there are many new both technologies and problems around us that need solving. And I think all of us think so much, right? So we think different things. So we're all very individual. We are different individuals, and so I think it makes sense to just when you're thinking about something, it could be anything. Like I said, sports, music. You're reading something in the newspaper. You can just have this element of what is a program I could write to solve a particular problem I'm reading about, or I'm watching on the television, or something like that. So I think problems abound, and I think given the entire space of programs that is possible, we have barely scratched the surface. I think in 10 years, we'll be wondering how we did without whatever are the imperative programs at that time. Just like the programs that we depend on today were not probably there even 10 or 15 years ago.
Yeah, so I think these questions will come from our real life interactions and our experiences. Okay, the next question is from YouTube. It says, what's the difference between a system programmer and an application developer?
So a system programmer usually works on infrastructure code. That means they write code that provides services to other pieces of code. While as the application designer will sit on top of systems layers. So I mentioned the layers briefly earlier, like instruction set, operating system, virtual machine, runtime environment, and so on. So systems programmers would work at this level, and typically they would be doing they would be providing services that are used by many different applications. So think of it like people who run your electricity grid today are systems people. So if something goes wrong, then a lot of things go down. And it's sort of an engineering challenge to keep those systems reliable and running and so on. The applications are what you do with the electricity that flows into your house, right? Then those applications are kind of unbounded.
Right, yeah. So the next question is, what is the easiest computer language to learn in a business? Is there one?
Obviously nowadays Python seems to be the most popular one. Easiest is also sometimes a function of, what are the resources you have available to help you learn, and also, of course, what you want to do. At the high school level, you might have heard of things like, Scratch and so on. So those seem pretty easy to learn, but they're limited, relatively limited in what you can do with them. At a slightly higher level, perhaps Python is very powerful and is easy to learn, and there are a lot of resources. Personally, I think JavaScript is very easy to learn and is a very good language because the number of different things you have to learn in it is very small. There are only 6 or 7 primitive operations, which makes it very simple and elegant. And the other thing with JavaScript is it just runs in every browser. So it's just available and you can deploy it and send it, share it with others very easily.
Yeah, so Python and Java surely, yeah, I think good to start with. I
Java,
think we just
JavaScript actually,
JavaScript.
not Java. Java is a little more heavyweight.
Right, yeah. So I have few more questions, but then I'll just maybe take last 2 questions. One is about any book you would recommend to study programming from scratch. And the other one is, can you highlight some of the projects done by UG students? So I'm assuming they're asking UG student at Ashoka. So you can.
Particular books, when I mentioned the Beautiful Code was one book, but also mentioned Programming Pearls. If anyone is familiar with that book, it's quite an old book by John Bentley, but has a few classic algorithms, various books by the pioneers like Cunningham, Ritchie, and Thompson, who developed the original C compiler and the Unix versions at AT&T. They have written some very good books on general programming. Now, today, of course, very few of us really work on completely self-contained general programs. We always, integrate with libraries, or we're always in some environment, or we're part of some larger system and so on. So again, it would depend on what exactly you want to do with it. But those books I mentioned, there are specific books I like on specific languages, of course. In JavaScript, there's JavaScript, The Good Parts. In Java, there's a book called Effective Java by Josh Block, which is very good. And similarly, like different languages will have particular books that are very good for it. And your question about UG projects. So I haven't guided any UG projects in at least 2 years, so I'm not up to date with the latest. But a couple of projects I can mention were 2 years ago, we had 3 students who worked on on crowdsourcing pollution information in a city via a distributed set of sensors. And this was a joint project with Microsoft Research, which was very interesting and very timely. Talking of problems, Bhavesh, pollution is obviously a very pressing problem, unsolved problem. So that was an interesting approach, I thought. Before that, I had a couple of students work on envisioning a modern browser that was, all of us have a lot of browser tabs open all the time. And so how would you better organize, search through those tabs, make it more task oriented? And that was a research project. And now we're actually seeing some of that in actual browsers as well. And there are many other projects, particularly in the HCI courses. There are a lot of interesting projects that UG students come up with.
Yeah, I remember the first project which you mentioned with Microsoft. The paper won the Best Paper Award.
Yeah.
Okay, thank you again, Professor, for such an enriching and engaging session. With this one, we come to the end of today's session and Scientifically Speaking Season 4. Before leaving, we would request our audience to please take a minute to share your feedback. The feedback form is available in the chat box. I would like to inform our audience that applications for the undergraduate program starting in August 2023 will open this month on 17th October 2022. Please note that registrations for the same are already open. We would encourage students to register early and submit their applications in round 1 to get an early admission and financial aid decisions. That is by January 2023. Without having their 12th board marks or CUET, that is Common University Entrance Test. They will also receive personalized guidance and mentorship by our academic counselor to help them through the process. Ashoka offers BSc honors programs in pure majors including physics, biology, chemistry, mathematics, computer science, as well as interdisciplinary majors in computer science and entrepreneurship, computer science and mathematics, and computer science and philosophy. I would also like to invite our audience for a webinar, The Ashoka Experience, a transformative journey at Ashoka's diverse and enriching campus on Friday, 14th October at 6 p.m. In this session, you will get a chance to interact with a group of Ashoka undergraduate students who will share their experiences of campus and residence life, talking about the various clubs, societies, sports, hostel life, dining, and cafes, and the overall environment in and around the Ashoka campus. The link to register for this webinar is provided in the chat box. With that, we come to the end of this session. Thank you once again for joining us. We look forward to your participation in the webinar on 14th of October. Thank you.